We're here for ARC313. My name is John Fermento. I'm a principal product manager in the Resilience Infrastructure and Solutions team. We build Application Recovery Controller as one of our services. So if you heard of that, awesome. If you haven't, check it out. It's a recovery tool to help you with the resilience. I'm fortunate enough to have Mike Haken and Mike Golofnik to co-present with me. They'll each introduce themselves as they come up. A couple of housekeeping things. If you haven't seen this, we recently released the resilience lifecycle framework. If you grab the QR code, you'll get access to the white paper. The genesis of this is over the last year or so, a lot of customers had asked us, where should we start in our resilience journey? And this white paper kind of outlines some steps in a framework for you to use. And then our session today will really focus on the design and implement and operate stages of that lifecycle. And then to quickly call out, AWS has a bunch of resilience-oriented offerings. I'm not going to go through each of them, so maybe just grab a picture and you can Google and check out the ones you're interested in. But I will do, again, a shameless shout out here to Application Recovery Controller. Definitely check that out. So to kick off our presentation, has anyone ever heard of the missing bullet hole story or knows what this is? All right, so a few of you. All right, so this was a new story to me. My friend Mike told me about it just only a couple months ago, so I'm very late to the party, but appreciate the folks that raised their hand to humor me here. So this is a P-38 Lightning long-range fighter plane. And in World War II, it was advantageous for the US government, right, to keep these in the air and be able to return home safely and do their duty in combat. And one of the things they needed to do was, how do we make these planes more resilient? And you're probably wondering, why am I talking about this during a talk about like distributed systems and resilience? And there's definitely some correlation here that we'll touch on. So just give me a second. But yeah, the goal is, hey, we need to keep these in the plane, right? And there's an inherent trade-off between armoring an aircraft like this and its ability to be agile, fuel consumption, and so on and so forth. And so the government had a team, the statistical research group, and a guy by the name of Abraham Wald. And this guy was like the typical smartest guy in the room. And the folks came to him with this problem. We need to keep these planes in the air. We need to add armor to them, but we need to understand the trade-off of where to place the armor, right? Because all those things, again, the adding weight, maintaining agility, maintaining proper fuel consumption, you need to weigh that with making sure that they're operable and getting our pilots home safely. And so the group came to Abraham with the data that kind of showed this distribution of bullets on these aircrafts when they were returning back to base. And the initial thought was, hey, let's put some armor where the bullet holes are. And Abraham tested this assumption. He's like, this just doesn't seem right. And he, being a mathematician and a statistician, basically said, let's look at this as an equation. And if we set the probability to 0, that if a bullet hole were to hit at the engine, as an example, we assume that it's not returning home. So if we set that, where would the bullet holes, where would that distribution end up? And then it ended up looking something like this. So what he determined was where the bullet holes were in the engine and the pilot compartment, things like that, they weren't returning home. They were shot down. And so that really focused the attention on the critical parts of the system. So again, really had to test the assumption. And like a leadership principle at Amazon, dive deep to understand where we need to be thinking critically about the resilience of our system and make the right trade-offs. And so they ended up adding more armor to these places. And so with our systems, we need to do the same thing. We need to peek around corners and understand where the vulnerabilities are in our system and make the right trade-offs on a variety of factors. And I'll show some trade-offs in a second, but to make sure that we're getting the most value out of the resilience that we're building into our systems. And so that takes us to the resilience analysis framework. This was a joint effort by a few folks over the last year of culminating essentially customer and internal conversations around how we can make our systems more resilient. And we defined a model that looks at common failure modes or categories of failure that we've seen. And so I'm going to talk about the theory of the framework and what you need to do to analyze your systems. And then Mike Haken will talk about some real-world customer examples of scenarios that we were involved in and how we use the framework to implement whether it's a corrective or preventative mitigation to increase the resilience of that. And then Mike Golovnik will talk about how our team, Application Recovery Controller, has operationalized a framework like this. So why should you care? First off, I'll say there's a lot in the white paper, the QR code will take you to that we won't cover. But the reason why you should care about this is it provides a repeatable process that you can use to assess and basically increase the resilience of your workloads. And that way, you can use it across your organization or various workloads, and you're using the same framework and the same process, and it becomes repeatable and something that you could operationalize and use it maybe weekly, quarterly, monthly, or whatever cadence makes sense for you guys, and Mike will share a little bit more about how we've made it work. It also guides towards recovery-oriented architectures, where you think about a particular failure category, and then how a mitigation can help a slew of failure modes across that category, and then help guide towards the right mitigations and the right observability strategies to align with your resilience goals. Excuse me. So to start off with this, we modeled or thought through what are the desired resilience properties we would want for our workload. And the first one is fault isolation. We want to intentionally build fault isolation boundaries that allow us to scope or limit the blast radius of a potential failure. We want sufficient capacity. We want essentially the workload to be able to handle the demand that is being thrown at it, if you will. And this could be CPU cycles, memory, you name it. We want timely output. And this essentially means that when a client makes a request, that they're getting the result or the outcome of that in their expected time frame. And that could essentially mean the difference of a client timeout being exceeded and the application being perceived as unavailable versus getting it within the appropriate timeout. Correct output. Essentially, we want the expected outcome, right, of the system. Sometimes incorrect or incomplete results, if you will, are worse than returning nothing at all. So we need to make sure that our systems are providing the output as expected. And then redundancy. Two is sometimes better than one, right? So if a component fails, we want to make sure that we have redundant or spares to take over in the event that there is a failure. And so taking those categories or desired resilience properties, we created the SEAMS model, and it just stands for shared fate, excessive load, excessive latency, misconfiguration bugs, and single point of failure. And each one of those failure categories violates one of the resilience properties. So shared fate, that goes beyond or spreads across your fault isolation boundaries is not necessarily a good thing, right? If you have a fault container that you're expecting to be able to use as a blast radius like mitigation, and a failure spans multiple fault containers or fault isolation boundaries, that's not what we want. Excessive load can go and violate sufficient capacity where all of a sudden maybe we're getting a spike in traffic that we didn't anticipate, and how can we handle those types of failures? Excessive latency could be a number of different ways that can manifest, whether it's a network device failure or slow hardware or whatever it may be. But how can that make sure that we are having timely output and not exceeding client timeouts? And misconfiguration bugs, I'll just call this out. This is probably the most popular failure category we've come across. But how can deployment failure, someone going in and changing a security group on accident, or patching an EC2 host, cause essentially the output to not be as expected? And the last one is single points of failure, right? We just want to minimize any single points of failure in our systems that could cause our system to be unavailable if that component were to fail. And so now that you understand the failure categories and the desired resilience properties, the first step in actually using the framework is understanding the workload. And this is just an example of an in-app purchase validation, a solution that someone built on AWS. And we typically start with an architecture diagram like this with numbers that kind of show the data flow or the life of a packet or a transaction, if you will. And then we also really want to break them down into atomic user stories. different functions that the system provides. And this is a very simple, simple system, if you will, right? It's a few services and 2 flows. But you can imagine in an e-commerce website or a retail banking website, the user stories are much more vast than this. But here we have a user story for in-app purchasing and then a user story for refunds. And what this allows you to do is prioritize which user stories are most valuable to your business and focus your resilience analysis work on those user stories. So you're not trying to boil the ocean. You can make meaningful progress with your analysis. So that's kind of the first step, is just understanding the workload and figuring out where we're going to focus. And within those user stories and diagrams, you really want to make sure that these 4 components are called out. And the first is your code and config. And you can think of that as your application code or any kind of configuration that is used for your system. The second is your infrastructure. So any of the AWS services or on-prem components, really anything that is kind of driving your system. Then your data stores, databases, EBS volumes, anywhere a state is stored. And then any external dependencies. And these could be a team within your organization that you're consuming an API. It could be a third party like ISV API, as an example. Maybe like you need weather data for your system. Like that would be categorized as an external dependency. And the main point to have this is we don't really necessarily care about making sure like, oh, do we have the database components called out? But the point of this is more as you're thinking through and diagramming and understanding your system, make sure you understand that the place of these components in there and then their interactions with one another. And you'll use that as part of the analysis. So now you understand the workload, you have it modeled right and diagrammed, and you're kind of, with the group you're working with, have a common understanding. Then you need to think about how we're going to use that framework, the seams model, on a workload to mitigate some potential failures. And then the first part of it, after you've start asking questions around those failure modes we talked about, is figuring out the trade-offs you need to make. And this is the same for Abraham with the aircraft, right? For our systems, the first is usually there's a cost and effort component here. And this could be, we talked about redundancy. Adding replicas or spares increases cost. There's an effort of implementing some advanced resilience patterns. And Mike will talk about some in a few minutes. There's also complexity involved, where you're going to have maybe advanced CI/CD systems to deploy in certain ways to help reduce misconfiguration and bugs, or you need more enhanced observability to understand different failure modes and be able to detect things more of a leading indicator than a lagging indicator. There's going to be increased operational burden, where you need to have more sophisticated runbooks, on-call process, making sure that teams know what they need to do in an event. This all is a trade-off that you're going to need to make on your critical systems. And then the last is consistency and latency. A lot of times, these systems tend to start thinking about a multi-region approach or having a DR strategy, and there's usually a typical trade-off of consistency over availability once you start to think about CAP theorem and asynchronous replication, but a trade-off you're going to need to reason about. So now you saw seams, the failure categories. You looked at the workload. You start to understand how those failure modes can manifest. We looked at some of the trade-offs of maybe implementing a mitigation. And then now you need to think about, if there is a particular failure mode that you've kind of reasoned about, you need to think about what is the likelihood that it could happen, all right? Like, should we invest our time in this particular failure mode? And likelihood is all about the plausibility that this could occur. And if you think about, for example, if you have an EC2 instance, over the lifetime of that instance, you're probably going to patch it. You're going to have maintenance on it. There's a decent likelihood that at some point, something's going to go wrong and that instance is going to be unavailable. Now, on the flip side, if you're using RDS and you have multiple replicas, there's probably not a high likelihood that that's going to be unavailable, because if something goes wrong, you have the replica to take over, and you're good to go. The other piece is impact, where you want to understand the harm, if you will, or the reputational or commercial damage of that failure mode manifesting. And so thinking about how likely it is to happen versus the impact of it happening, you can make a judgment on which failure modes to focus on and continue on with developing mitigations for. And just to kind of show here, there's typically like a point of diminishing returns, right? You can kind of eke out So much more resilience from time and effort in taking those trade-offs. And kind of as you get to the top of that curve, it's usually reserved for more of our critical systems, where maybe if you have an internal, in your organization, like an internal directory to look up folks, you probably don't want to spend a ton of time and effort making them very resilient. But if you have a system that's critical to your business and driving a lot of revenue, you probably want to focus more on the resilience and specifically the critical user stories that are driving your business. So the next part is, now that you've figured out the failure modes, you know where you want to focus, you need to think about how you would observe these things. And you really want to have leading indicators and lagging indicators if you can. Leading indicator being you're being aware that something is changing in the system and you're approaching a threshold that could cause an unavailability scenario, but hasn't happened yet. So an example of this could be monitoring connection count of a database and understanding it's getting to a certain threshold where you could then maybe implement throttling or terminate some least used connections to stop a potential issue from happening, where a lagging indicator would be an alarm on connections failing to the database, as an example. But again, we want to have both metrics available to you if you can do that. And so now that you understand how you'd observe them, we need to think about how we would mitigate them. And there's kind of two common approaches, preventative or corrective. Preventative meaning I'm going to put a mitigation in place that would stop an outage or a failure from occurring. And you can think this of like maybe you have an excessive load on your infrastructure, maybe you have throttling or load shedding to protect the system. So you never get to the point where the system's completely unavailable. Or corrective mitigation, as an example, may be where you're starting to see a load in traffic and you understand that you're going to get excessive load over the next 24 hours. And then maybe you correctively auto-scale to start adding capacity as you can, would be an example of that. And so yeah, with that, I'm going to pass it over to Mike, who's going to share some customer examples. Thank you.
Thanks, Sean.
Yep.
Faster. A lot of the details have been anonymized.
20 minutes? 15.
So let's take a look at a couple of these, how we actually use the analysis framework to find resilience threats and then provide mitigations for these customer workloads.
It's quite clear. You've been doing it multiple times, this presentation.
Resiliency.
Cool. Good job.
So they are containerized fleets, and it had a sharded database. And each node in that sharded database.
Yeah. By the way, I've created a little bit of a shadow on the. No, I am.
And then the system had a metadata database. Mike isn't working.
Oh.
1 second.
Maybe it's another mic. No.
I thought he was telling me. Is it mine? Hello? Yeah, I think mine may be on.
Am I on?
No, this is mine. I was like, this guy's telling me I think you can hear me.
Maybe we got confused with two mics.
Oh, yours is
because
on.
I'm mic 2. Here we go.
All right. All right, you guys get to see me wave hands with a mic and a clicker. All right, hopefully this is better. So we have this sharded database, and we have a metadata database that maintains a map of the shards, right? And this is how the nodes in this fleet actually find which database they need to talk to. The containers themselves, the software would lazy load the mapping data from the metadata database. So when they've got their first request, they would reach out to this metadata database, get the mapping, and then connect to the database they needed to. So we wanted to ask the question about excessive load. In a normal scenario, right, the user would say, hey, I want to find Smith. And we'd go to that worker fleet, and the fleet would go to the metadata database. They'd return that database mapping, and we'd find that, hey, Smith, for the letter S, is on DB4, right, and we connect to the database. What about when this happens? We have a whole lot of people show up at once. They all try to do a lookup. All of the worker nodes try to connect to that single metadata database. and crashes it. Right? They had a really plausible excessive load scenario that would take down this entire system and make it unrecoverable. So what we suggested is looking at a pattern that we call constant work. So instead of looking up that metadata when they received the request, we could instead, say every 60 seconds, have all these worker fleet nodes pull that mapping from something like an S3 bucket. And so it looks like this. They just continually do the same thing. It's going to remove any unanticipated load because they're always doing the same thing over and over. So regardless of how many customer requests there are, we don't change the amount of load on the metadata service. So constant work has a couple of benefits. It gives us consistent, predictable performance, and it gives us this property that we call anti-fragility. And it means that when something goes wrong, when something breaks, we actually end up doing less work. Right? So when things go wrong in the system, we remove the amount of work being done instead of increasing it. So constant work could help them solve this excessive load problem with that metadata database. But like John mentioned, we're going to have to make trade-offs when we want to try to improve resilience. And so one of the trade-offs with constant work is that we're going to have potentially wasted work. Right? We're going to do a lot of work even when things may not have changed. So we have to accommodate for that and understand what is that going to increase in potential costs, right? Because all of those requests have some cost associated with them. The data transfer has some cost associated with it. So we need to consider the trade-offs there. Is the resilience improvement of implementing constant work to solve this problem worth the trade-offs we make? So as our first example, our next one is a customer that wanted to set up a multi-region synchronous replication system. So they had a desire to meet an RPO 0, so have a 0 recovery point objective, which means no data loss across regions. They were going to use multi-region synchronous replication across 3 different regions. And John mentioned CAP earlier. Has anybody heard of the CAP theorem? A couple people. So what the CAP theorem says is that there are 3 properties: consistency, availability, and partition tolerance. And you can only have 2 of the 3. And so in most distributed systems, we all have to accept partition tolerance because we have multiple servers, multiple components, which means we have to make a trade-off and choice between consistency and availability. Well, this customer wanted to try to beat CAP theorem. Right? They said during a failure, when one of these things wasn't available, we're going to update the configuration to remove the impaired region to return availability. Right? Because in a synchronous replication scheme, if any one of the nodes fail, the entire system fails. And so they wanted to make a runtime update to this configuration during a failure. Once that region recovered, they wanted to sync data back to the impaired region, meaning that they would have some period of inconsistency anyways. Right, and so they wanted to try to achieve all these at the same time. And what we came up with when we looked at it, right, that this was a really complex system that was going to be fragile. And ultimately, we wanted to test the cascading failures part of this. Do we have shared fate, right? So we were looking at how this replication affected fault isolation. And so here we can see we've got our 3 regions, region A, B, and C, and we're using sync replication. And so if region B is impaired, is having a bad day for whatever reason, maybe that database node failed, and a user goes to do a write in region A, they can't. This operation fails. And so what this means is that we have cascading failure from region B to region A. And so then what they would do, right, they would take the impaired node, remove it from the replication configuration. And so this database then would be inconsistent until it was able to catch up after it recovered. So instead, we said, if you really do want fault isolation, if we don't want cascading failure, we could use async replication instead. And so now when region B is having a bad day, we can still perform writes in the other regions. We can still take a write in region A and asynchronously replicate it to region C. And then when region B recovers, we'll have some catch-up replication to do, but it'll eventually get back to a state where it's caught up, with some minimal lag in that asynchronous replication. So to achieve fault tolerance across those regions, prevent cascading failure, we were planning to use async replication. And so that one helps reduce latency because we didn't have to wait for all of the writes to be replicated to both regions. So asynchronous replication is going to give us faster performance, and it gives us improved availability. Right? We could still take writes and reads in the remaining regions even when one of them was impaired. But our trade-off here was consistency. Right? We made a trade-off on consistency saying that we weren't going to be able to achieve an RPO 0 in this type of scenario. Right? We'll have to deal with some inconsistency. And we decided because even in the original design, it already accounted for an inconsistent state. Right? When one of those nodes failed, it would still have to catch up. And so we made a decision, right, to accept that potential amount of data inconsistency. It's not really data loss. Right? That data still persisted on a database in the primary region where it's written. But if we had to fail over, we might have to deal with a period of time, right, where we didn't have all of the data available. And so that was one of the trade-offs that we had to make. All right, let's look at example 3, a distributed storage system. So this service has data sharded across multiple storage nodes. The data is replicated across those nodes. Read requests issued by the users of the system could land on any one of the replicas. And the requests are generally routed to a random storage node from front-end request routers. So what does this look like? So user performs a read, and they end up landing on one of the storage nodes. Right? They may issue a second read, and they'll go to a different node, right? Potentially that node. But what if one of these nodes is slow? Right? We wanted to ask, what happens when we have excessive latency in the system? Right? So it's possible this storage node on the bottom, maybe it's experiencing a hard drive error, right? Maybe it has a faulty CPU, faulty memory. For whatever reason, it's responding a lot more slowly than the other storage nodes. And so the result here is that some percentage of our reads are going to be measurably slower than others. So our tail end latency, maybe it's P90, P99, P99.9, but that tail end latency is going to be significantly higher, right, compared to the other nodes. So we suggested using a pattern called hedging to reduce tail end latency. And so what hedging is, it's a way that we send requests in parallel and race them against each other. So now we've got that slow storage node again, but we're going to send two requests, read requests in parallel. And so you can see the one on the top ends up being a lot faster than the one on the bottom. And so in hedging, we just take the fastest response. And so now when that slow storage node, right, responds at that higher tail end latency, we actually don't care about it because we got a faster response from our other request. And so hedging gives us the ability to reduce tail end latency. It also masks transient failures because now that storage node being slow or being completely unavailable are exactly the same to the client, right? They don't know if that thing was slow or if it just failed to respond because they were only looking for the first response, right? And so they take the fastest one. The challenge with hedging, right, and our trade-off is that we're going to be doing additional work. Now instead of every one read request, we're going to make 2 requests or 3 requests, depending on how much you want to hedge. Right? And so that's going to be additional work, could potentially be additional cost. And the other thing that you have to be really careful with hedging is that those requests have to be idempotent. And what idempotent means is that whenever you issue the request, no matter how many times you issue it, the same result always occurs. So read requests, by their nature, are idempotent. So you can do this for reads. Write requests or mutating changes, some can be idempotent, some may not be. So you have to just be careful with how you would implement hedging in a system. All right, let's look at our 4th example, multi-AZ deployments. So we have a system that's architected to use 3 availability zones. For the customer going into this design, deployment speed was a priority for them. And the deployments target instances in each AZ at the same time. They had built the system relying on the success of the pre-production environment to validate the deployment. But what we actually found is that in many customers, their pre-production environments don't exactly mirror production. Does anybody here have a real pre-production environment that exactly mirrors production? I see, I think 3 hands, 4 hands. So you see, most customers, right? There's some disparity between those environments. And so what happened was when they'd make a deployment and it would go bad, right? Maybe it was a bad change, maybe there was something in the environment, maybe something that they didn't catch. And they push that change and it goes out to get deployed. It hits all 3 availability zones at the same time. And we have this large-scale failure, right? And we wanted to ask, are the changes we're making, are those deployment units at least as small as your intended fault isolation boundaries? And here, an availability zone provides you a fault isolation boundary. We don't expect failures in one availability zone to cascade to other availability zones, right? Instances fail in one AZ don't affect instances in another AZ. So instead, we looked at, can we make our deployment units aligned with availability zones? So now when we push a change and it goes to deploy, it goes to one availability zone. And if that is bad, right, we have a failure there, we have a number of things that we can do to correct it. If we've built an availability zone independent architecture, which means that we keep all of our traffic inside an AZ, we could use something like a zonal shift to move traffic away from that AZ and really quickly recover before we've even been able to roll back the deployment. If we don't have an architecture that's built that way, we could certainly initiate an automated rollback based on some metric or alarm. But the key here is that our remaining 2 availability zones haven't been changed and aren't failed, right? And this doesn't have to be a complete failure, right? This deployment doesn't necessarily mean that we have touched every single instance at once, but it could be that we've touched an instance in each AZ at the same time, which expands the blast radius of a failure. So now when we deploy and we see a success, we can go one AZ at a time and make that a dependency, right? Make that a gating check before we move on to deploy to the next availability zone. And so using fault-isolated deployments gives us a predictable deployment failure blast radius. We know that our blast radius will only ever be a single availability zone in size. And it helps us preserve the customer experience, right? By being able to quickly roll back or shift traffic away from a failed deployment unit means that we can keep serving the customer experience that we were trying to deliver without a large-scale failure. But our trade-offs. Our deployments are potentially going to be a little bit slower, right? We have to deploy to an entire AZ at a time, watch it, inspect it, make sure everything's healthy before moving on to the next one. It's also going to be a little bit more complex to orchestrate, right? You have to be able to set up your CI/CD system to be aware of what AZ it's deploying to. Now you can do this with something like code deploy and tags. So if you tagged all your instances with an availability zone ID, you could set up individual deployments for each one of those. But it could be a challenge, right? It could be a complex thing to orchestrate within a CI/CD system. So last example, an e-commerce site with multiple dependencies. So the site uses multiple backend services to deliver content on the web page. Not every microservice is critical to the customer experience. The web service currently, though, requires that each component has to load in order to render the whole page. So here's our web page. It's very fancy. So we have product pictures, right, calling one microservice. We have our add to cart functionality. That's another microservice. We have suggestions on things that are frequently bought together. We have a section for items that you might be interested in. And finally, we have new promotions. But now, if the new promotions microservice fails, the whole website fails to load, right? That's not a great customer experience. It's not what we want. So instead, If all these microservices successfully load, we can still serve the critical user story here, right? The most important thing is that the customer can see what they want to buy, add it to a cart, and check out. So if new promotions isn't available, we just don't render it, instead of failing to load the web page. This is the idea of graceful degradation, right? We can gracefully degrade when components of the system are slow or unavailable. And so graceful degradation helps us prevent cascading failures, right? Again, like we saw earlier, we don't want a failure in that new promotions widget to impact the checkout, pictures, and so on. And that gives us the ability to provide a partial customer experience. But again, we have trade-offs. And being able to implement graceful degradation means that we really have to understand our dependency interactions. Understanding the dependency map across an entire service and orchestrating it to be able to gracefully degrade can be challenging, right? So it takes a really deep inspection of how all of your components work together. All right, so those were our examples that we've seen in real life with customers where we've used the analysis framework to find potential resilience gaps and then suggest mitigations to be able to solve them. So I'm going to hand it over to Mike, and Mike's going to talk about doing resilience analysis at AWS.
Thank you, Mike. And let's see if my microphone works. It does. Great. So my name is Mike Golovnik. I'm a senior software engineer at AWS, and I work at the Resiliency Infrastructure and Solutions organization. I will tell you about how my team and I implemented RAF in my organization. I will share some of the lessons learned, and most importantly, I'm going to help you answer the question if you should implement RAF in your organization. One service where we implemented RAF is the application recovery controller routing control. Customers use routing control to recover applications from regional level infrastructure or application failures. They use routing control to initiate a failover and update DNS records quickly and reliably. This diagram just shows one of the customer architectures. Routing control offers 100% SLA. It is designed to operate even in the most extreme scenarios, like 2 regions are impaired, or 1 region is partitioned away from another region. Another service where we implemented RAF is zonal shift, which is also like routing control part of the application recovery controller. It is designed to help customers like you to recover your applications from impairments within a single availability zone. Zonal shift is free, and it is integrated with AWS ELB, which makes it very easy for you folks to shift traffic away from an impaired availability zone without taking any control plane dependencies. So on this diagram, a typical multi-AZ application is seeing elevated error rates in AZ3. And the customer goes and uses zonal shift API to shift traffic away from the EC2 instances in the AZ3 to the other availability zones. And behind the scenes, zonal shift flips DNS records in Route 53 without taking any control plane dependencies and in a constant work manner. So which means that it doesn't matter how many customer requests there are or how large the applications are, it will still work. So zonal shift runs at a large scale, millions of load balancers, millions of resources, and it creates value for you at the time when there is bad weather in the availability zone, all while running in the region where the availability zone might be impaired. So it is obviously challenging to operate and continue to build features in such a service, and it is not a surprise that we chose to apply RAF to think about resiliency of the service proactively. So as John mentioned, resiliency comes in all sizes and shapes, from airplanes to applications. In the case of zonal shift, it must work at the time when there is an availability zone impairment. That is what it is about. You, our customers, must be able to rely on it at the time when planes of other AWS services might be impaired. So for many applications, the biggest resiliency concern is availability, which is often measured in failure ratio. Now, not so much for zonal shift. While we really care about how many 500s you see, we prioritize your ability to start a zonal shift. So perhaps if the very first request to start a zonal shift fails, maybe it is okay as long as the second request, the first retry, succeeds. It is important to understand what is truly important to your application. And it is never simple, of course. Durability, consistency, availability upstream, availability downstream. You should clearly define your customer workloads first, and then work backwards from what is important to these workloads, resiliency-wise. So the process that we institutionalized in my organization is that we meet every other week. We have a defined agenda, but we also have a facilitator that is responsible for adjusting this agenda to the particular meeting, to the particular conversation. We have product folks in the meeting, but the process is driven and owned by the engineering. So as we go through the process, we end up with a number of documents. At Amazon, we have this culture of writing that we believe is important. And by taking the time to write the failure mode documents and reviewing these failure mode documents with the team, we gain deeper understanding of the problem than if we had just talked through it. So you are listening to me and I can hear you thinking, well, this RAF thing, it's heavy, process, documents, and you are right. RAF requires substantial investment of engineering effort. But you operate a critical application running reliably at all times. Your application is complex. It has miscellaneous dependencies, and it deals with constantly changing customer traffic. So let me ask you one question. In your software development lifecycle, do you dedicate time to thinking about resiliency proactively after the application launch? I have no doubt that all of us do retrospectives after events. one of the reasons that we institutionalized RAF in my teams is that we wanted a more proactive way of thinking about resiliency for our critical services. We remind ourselves that resiliency is not a destination, it is a journey. We cannot just design resiliency once. Now, what did we learn from the RAF from this implementation? It is no surprise that just like as any other initiative, RAF requires executive level support. It is also not a surprise that RAF needs engineers that are willing and able to dive deep into hypothetical scenarios and reason about them. That, of course, gets down to having the right people on the team and that have passion towards resiliency. So we learned that RAF is a process for engineers just as much as it is for stakeholders. It helps engineers learn about the behavior of their systems and develop a resiliency mindset. But RAF becomes fully fruitful when it is integrated with your ops and feature development processes. But you have to commit resources to not only executing the program, but to also improving your systems in the areas that your team identifies as the most important. So let me share an example from my team. One day, our on-call engineer mitigated a deployment issue in one of our application component environments. While mitigating that issue, they realized that the root cause was in the intermittent failures of a non-critical dependency. Okay, the engineer called this out during our regular RAF meetings. We reviewed the failure mode documents with the team, had a conversation, and we realized that the probability of this non-critical dependency of slowing down our ability to scale up the application quickly, that probability is higher than we originally thought. Which means that some of the specific failure modes have higher risks than we have originally thought. So, as the result, we reprioritized the work to remove this non-critical dependency from the application start critical path. Now, if not for RAF, then this risk would have stayed with us longer. So let me now summarize. You are operating a mission-critical application. You greatly care about running this application reliably at all times. Your architecture follows best practices. You have well-designed SOPs, standard operating procedures. You have stellar operators, but your application is complex. It deals with constantly shifting traffic patterns, because customers do different things. It has miscellaneous dependencies. So if you see value in thinking about resiliency proactively, and if you subscribe to the idea of resiliency is a journey, not a destination, then you should consider implementing RAF. Now, once you do, please trust that your team will identify opportunities to improve your application. And your team will expect that you take the advantage of those opportunities. Thank you for your time. And the three of us will, thank you.